Okay, 12th class, third chapter, current electricity, 21st session. Application of potentiometer to compare the EMF of two cells. To compare EMF of two cells. This is the first application of potentiometer to compare the EMF of two cells. See, last class I introduced the basic principle behind the working of potentiometer, which says that the potential difference developed across the length of the wire is directly proportional to the length itself. If current is made a constant, and the wire should be a uniform cross-sectional wire. So first of all we should create the potentiometer circuit, and the primary circuit of the potentiometer is nothing but a source which gives a variable source of EMF, right? I told you, just like a 10-meter wire. A 10-meter wire tied like 1 meter, 2 meter, 3 meter, 4 meter, just like that. Again on a wooden plank, something like that. And it is connected with a cell, source cell, so that the current should flow through this, right? I told you current should flow through that source cell. So this is a source cell, EMF E. And to adjust the value of current, if you don't need very high value of current, suppose you are using a very high EMF and you don't need that much high current through this, you can use a rheostat. Rheostat means a variable resistor. By adjusting the rheostat, if you give more resistance here, the current at the wire will be decreased. So simple. Why? Because the effective resistance will increase. Here you say if you increase the rheostat wire, no, if you increase the rheostat value, what happens? The effective resistance of the circuit increases. If the effective resistance of the circuit increases, current decreases. So you can adjust the current through the wire by adjusting the value of rheostat. That's all. So that's why we are using this rheostat. Again, you can use a key and all to adjust, to control the circuit. This is what the basic of primary circuit of the potentiometer. Now by adjusting the rheostat, you can make a fixed current to flow through this wire. Once the experiment started, you should not change the value of rheostat, because we need the current to be constant after that. Once you started the measurement, the current should be constant throughout the length of the wire. So this is the primary circuit of the potentiometer. Now if you switch on the key, what happens? If you close the key, what happens? Current will start to flow through the wire. A fixed value of current will start to flow through the wire. That is what is happening now. Now what next? What next is the secondary circuit. Secondary circuit should be connected like this. EMF has a positive connected to this point. Again, we have a 6-way key. This is a very important thing. We have a 6-way key. We have a 6-way key. Now through this one way, between 1, 2, if I say it like 1, 2, 3, 4, 5, 6, let me name like this. Just simply naming, that's all. Between 1 and 2 there is a cell of EMF E1, and you should connect positive to the positive, right? So that's all. And this is what? E1. And next to between 5 and 6 there is another EMF E2. Actually we have to compare E1 and E2. Again, the connection should be like positive connected to positive. It is must. Otherwise you will get wrong answers. Next is the galvanometer, right? And the variable contact jockey. That's all. Now what happens? Okay, and I told you this again is fixed on a wooden plank. Below that you will have a scale, and through that scale you can measure the length of the wire. You can measure the length of the wire, something like this. This is the scale. Now what is happening here? First of all, you connect between 1, 3 and 2, 4. Okay, you make the connection over here. First you make the connection over here. See, when you're writing the exam, you have to say it in words. Connect between 1 and 3 and 2 and 4. Then what happens? E1 will be coming into the picture, or E1 will be coming to play. And we will move the jockey. So actually, first you should touch the jockey here. Then galvanometer will show deflection in one direction. Next you have to touch at the other extreme, here. Then the galvanometer should deflect in the opposite direction. I told you there is 0 at the middle. There will be one side deflection, other side deflection. First you have to connect jockey at this point. Then suppose it is deflecting like this towards left. Then you have to connect at this point. Then the galvanometer should deflect this way. Then only there will be balancing happening in between. You just think, then you will find the answer why it happens. If I try to explain it, it will become more complicated. So I'm leaving that. It should be like that. Then only you can start the experiment to get the final answer. So that is to be done before you proceed the experiment. There should be deflection in both the direction happening at the two extreme ends of the wire. Now what you have to do is you have to connect it here, and there will be deflection in one direction. Slowly move it, jockey. So slowly moving, you will start decreasing the current, yes. So slowly moving jockey over the length, okay. Slowly moving jockey over the length, slowly moving over the length. Galvanometer will start to decrease the value, yes. At a particular value, at a particular position, galvanometer will be at the 0, means that is the null point. And you should measure the length to that much length. You should measure that much length. How? See, L 100, 200, 230, suppose something like that. So you can measure that length L. Now, what do you mean by L now? Which means this battery, ready? This battery is balanced, or this EMF is balanced by that much length of potential difference. I will explain it. This EMF is balanced, this E1 is balanced by a potential difference which is developed in that much length. Suppose it is L1 length. Okay, so this E1 is balanced by the potential difference developed across that much length. So you can say E1 is equal to L1E. Yes, L1E. What is E? What is E? Where E equal to potential gradient. What? Potential gradient. Potential gradient means potential difference developed per unit length. Potential difference developed per unit length. That is the meaning. Per unit length. That is what the potential gradient means. How can you find it? You can find it like E is equal to total potential difference across the wire divided by length of the wire. You find what is the total potential difference developed across the wire. You take a voltmeter and connect between these 2 points. You can find what is the total potential difference and divide it by the length of the wire, 10 meter. You will get 10 meter means 1000 centimeter. You will get the voltage per unit length. That is what we call it as potential gradient. So we got one equation, E1 equal to L1E. Now what you have to do is remove the connection between 1 and 3, 2 and 4. Remove it. Ready? Now connect between 3 and 5 and 4 and 6. Okay, you found the balancing length for the first cell. For E1 you found the balancing length. Okay, for the cell E1 you found the balancing length. Now what you have to take is take out E1, remove E1, disconnect it, and take the connection between 3 and 5 and 4 and 6. What happens? The cell E2 will start to play, or E2 came in contact with the primary circuit. Now again you do the same thing. You should connect it here, or you should touch it here. There should be galvanometer one side. You should touch the other end. The galvanometer should show the other side. Okay, now again you have to come back and touch it here. The galvanometer will be showing one direction, and you have to increase the length. So naturally, galvanometer needle will be moving towards 0 at a particular length L2. Again, at a particular length L2, again there happens the balancing. Suppose this length is L2. Suppose now, previously it was balanced here. Now what happens, like it is balanced over here. So you can measure L2 like 100, 200, 300, 300 something. Ready? 100, 200, 300, that much. Okay, so we have to find the new balancing length L2. Okay, let this much length, 100, 200, 300, 300 something, that much is equal to L2. So there you can say the EMF E2 is balanced by the potential difference developed across L2 length of wire. So E2 is equal to L2E. That is the new equation. Actually what we need to compare the EMF of two cells. So you can take the ratio. Comparing means taking the ratio. E1 by E2 will give you equal to L1E by L2E, and this EE is cancelled. So E1 by E2 equal to L1 by L2. So the ratio of the EMF is equal to the ratio of the balancing length. Means if you know any one of the EMF, you can find the other unknown. If you know E2, you can find E1 by measuring L1 and L2. If you know E1, you can measure L2 by measuring L1 and L2. So that's it. This is the comparison of EMF of two cells using potentiometer, which is the first application in your textbook. See, during the experiment, we should not change E. Means what? Potential gradient. What is potential gradient? Potential gradient is the potential difference per unit length. That should be made constant. That is possible if the current through the wire is a constant. For the current through the wire to be constant, this rheostat should not change. Once it is fixed, it should be fixed forever until the completion of the experiment. This rheostat should not change. Okay, that's it. Now one more thing I can give you as an idea. If the rheostat is very large, if the rheostat value is very high, what happens? Here resistance will be very high. So the total potential difference will be splitted as potential difference across the wire and potential difference across the rheostat. When rheostat is high, more voltage will be across the rheostat. Less voltage will be across the what? Wire. See, this is just like a cell. This is the wire. Suppose the entire wire is represented like this, and rheostat. The situation is like this. See, the entire wire I represent using one single wire. So the situation is like this. So if you increase the rheostat value here, the potential difference here will be decreasing because they are connected in series, right? Same current will be flowing through the rheostat and potentiometer wire. So when rheostat is high, current will be low, the potential difference across the wire will be low. So it will require more length to balance. Potential gradient will be less. Okay, such explanation you have to read it again and again so that you are getting some induced information about it. If I started explaining all this, it will confuse you. So let me stop it here. Just imagine these are two resistors connected in series. One is the potentiometer wire and the other is the rheostat. When rheostat value is high, current will be low. If current is low, the potential difference across the wire will be low. If potential difference across the wire is low, potential gradient will be low. If potential gradient is low, more length will be required to balance the EMF. That's all.